Here's what we're doing. We're talking more about graphs. Okay? Graphs of logarithms specifically. So we said one of the main ways that you can approach graphing logarithms is to just graph the exponential function, right? If you just graph the exponential function, which is usually easier, then if you find its inverse function, it will be some kind of logarithm. It doesn't work always, right? For example, if you were supposed to graph log base 3 of x, the inverse function there is not so hard, right? The inverse function here is just 3 of the x. But if you're graphing a more complicated one, like, I don't know, maybe maybe 2 times log base 3 of x minus 1, this one has a harder inverse function to find. Okay? To find the inverse function here, remember you switch the x's and the y's. You need to divide by 2. And now that we divided by 2, now we just have a logarithm. We can put it in exponential form. An exponential form that's 3 over x divided by 2 equals y minus 1, and then add 1. So this is a little bit more involved to find the inverse function of something like this. But again, there's also some like shortcuts for inverse functions, right? This is a vertical stretch by 2. Its inverse function has a horizontal stretch by 2. This is 1 to the right. This is 1 up. Okay, so there are some shortcuts for finding inverse functions. So that was one way that we talked about graphing logarithms, is you can just find the inverse function, and most people are more comfortable graphing exponential functions than they are logarithms. But anyway, we're on to example 4 today. Graph f of x equals 2 log base 4 of x alongside its parent function. Then find the domain, the range, in the equation of the asymptote. And again, because on the quiz, some people made a small mistake for asymptotes. Remember, if it's a horizontal line, that's y equals. That's for exponentials. If it's a vertical line, that's x equals. And that's the asymptote for logarithms. So watch out for that. Okay, so here we go. Let's do this. All right. So we need to graph f of x, and we need to graph its parent function, log base 4 of x. So what we can do for log base 4 of x, right? Right, this is the parent function. We could graph its inverse function first, 4 to the x. What does 4 to the x look like? 4 to the 0 is 1. 4 to the first power is 4. 4 to the second power is 16, etc. Right? And these dots are for the exponential function. So to graph its inverse, we just switch the x's and the y's. Right? So 0, 1 becomes becomes 1, 0 for the parent function. This 0.1, 4, right? That becomes the 0.4, 1 for its inverse function. This point over here, 1/4. I'm getting ahead of myself. This function, this point here, is a -1, 1/4. So for the logarithm, that'll be 1/4 -1. And this is our logarithm function. Okay? I'm not actually connecting the dots on the exponential function because we really want the logarithm function. Okay. And now we also have to graph. So this is the parent function. Right, this is y equals log base 4 of x, the parent function. We also need to graph f of x, which is 2 times that logarithm. So what does this 2 do? What transformation, what function transformation do we have here? How do we find f of x and graph it? What is the transformation we have here? I'm going to keep making weird faces until somebody answers. Maybe not. What function transformation do we have here? A vertical stretch. Good. Oh my goodness. It's something happening on the outside, which means it's something vertical. A plus on the outside is a shift. A multiplication on the outside is a stretch or a compression. Okay? So vertical stretch by 2. So we're doubling all of these y values. Okay? So what is the y value here? It's -1. 2 times -1, that's -2. Okay, so this is the y value of f of x. The y value on this point is 0. Double 0 is 0. This point's here as well. This point has a y value of 1. Let's double that. Now we have a y value of 2. All right. And we just connect the dots. And they look very similar. But this one's steeper, right? It rises quicker. It also falls quicker. So that's example 4. We did a whole bunch of things, right? First, we found what is the exponential function. And then we use that to find its inverse in red. Then we use function transformations to get this logarithm graph in pencil. If you had more than 2 colors, that would be even better, but I only have 2 colors here. Okay? Colorful pens, and then you can use colorful language to describe these functions. Oh, no, we're not done yet. Domain, range, asymptote. Okay? Domain. The domain of an exponential function is always easy. It's all real numbers. But remember that this is a logarithm, so it's inverse. So the range is going to be all real numbers, right? What is the lowest y value of this pencil graph? The lowest y value, well, it goes off to infinity. What's the biggest y value? Well, it also goes off to infinity. So the range is all real numbers. The domain, though, is not all real numbers, right? There's nothing going on over here. We only have positive numbers. Domain is 0 to infinity. And the asymptote is this y-axis. The asymptote is x equals 0. And now we're done. Okay, any questions on this? We've done 1 problem. We only have 2 more to go. And then we'll have a nice, chill, early Friday weekend time. Okay? All right, example 5. The weekend will come sooner, too, if people answer questions. Graph. Y equals negative log of negative x. And again, find the domain, the range, and the asymptote. So again, we can approach this problem the same way we approached the last problem, right? If we just start by graphing the log of x and then use function transformations, we could do that. And if you wanted to graph the log by graphing its inverse function, 10 to the x, you could do that as well. All right? So a lot of things that you could do here. What is the inverse function of this? Negative x, 10 to the negative x. Oh, I see. So either way, we do need to graph it. What I'm going to do, I'm going to do something a little different. Let's not do this with transformations. Let's do this and remember how to evaluate logarithms. Okay. We're going to do a table for here. A bunch of x's and their y's. So, recall, right? Y equals the log, common log right here. Common log, it has a 10 down here, we don't write. Has an equivalent exponential form. 10 to what power equals y? So if you wanted to do this just like we did example 4, you could. But this is the same problem, so I'm going to show you a different method of doing this by making a table of inputs and outputs. All right? So for example, we cannot plug 0 into this function. If you use your calculator, you plug in 0, you're not going to get anything. Right? But we can plug in negative numbers, because if we plug in a -1, for example, then we get a -1 and +1. So you can use your calculator for this one. It's a common log, right? If you use your calculator, what does it give you for the negative log of -1? If you type that into your calculator, it'll give you 0. Right? Can use a calculator for common and natural logs. Later on, we'll also show you how to use your calculator for anything. That'll be on Monday. So you just plot the point, -1, 0. And you can plug in another point. You could plug in -2, -3, -10. Plug in -2. Type that into your calculator. I do need to type this into my calculator. I cannot do this one in my head. Right? You get negative log of -2 or +2. You're going to get -0.3 approximately. And you can just keep on doing this. Plug in more points on your calculator. Let's try -5. You type that onto your calculator, you get -0.699 or about 0.7. Let's do some fractional ones. -1/2. What do you get? If you plug in -1/2 onto your calculator, you're going to get 0.301. Okay, so you just plot these points. -1, 0. We got that. -2.3. It's about here. -5 is about -0.7. About right there. -1/2 is +0.3. And it's kind of hard to see what's going on. Let's plug in more points, right? What about -10? Plug -10 into your calculator. You're going to get -1. So it really flattens out in that direction. What about -1/10? You plug that into your calculator. -1/10. And you should get 1, I believe. Yeah. All right. So you connect the dots. You still have this asymptote up here. And then it goes along this way, like so. And this is our answer. Again, whenever you're graphing, it's a good idea to check your answer, right? What function do we have here? We have negative log of negative x. Yeah, it looks about like we graphed it. Okay. Any questions for approaching things this way? Okay. Now let's do the last example. So the last example is going to be a good example. Because if you remember the last question from your quiz, it was pretty tricky. We're going to show you a different way of answering those questions. Okay? A different way that you may like more, you may like less. Okay? Find an equation of the following. Okay? And it's a transformed common log. All right? So it gives you that there's an asymptote at -2, has the points -1, 1, 0, 0, and 2, -1. Bless me. All right. And it looks in this shape. So it's some sort of transformation of a logarithm. So again, you should remember, right, this is a transformation of log of x. All right, what does log of x look like? Log of x looks something like this. So we need to figure out what transformations are being applied here. So first off, you should notice that the asymptote is going to a different place, right? The asymptote is not the y-axis anymore. The asymptote zoops over to the side. Okay, so asymptote being at -2 means we moved left 2 units. Asymptotes are a great thing to look for exponentials and logarithms. So we already know that we move left 2. What else do we know? We could look at the end behavior, right? Normally logarithms at the asymptote go down to the depths. This logarithm at the asymptote is happy. It's climbing to the skies. Okay? So it's going the opposite direction. Instead of down, it's going up. So it means we also know we have a reflection about the x-axis. What we do not know, and what really causes the problem, right? This is what we know. We do not know if there's a vertical stretching or a horizontal shift. Or a vertical shift. We know that there's a horizontal shift. And this is the same situation that we were in on the quiz, right? In the quiz, you could easily see the reflections, or most people could see the reflections. For exponentials, we could also see vertical shifts. We couldn't see the horizontal shifts, and that's what most people missed, or stretching. Here, it's an inverse. We see vertical reflection, we see a horizontal shift, but we don't know if there's any stretching or a vertical shift. So one way to do this is to guess and check. Another way to do this is to just say, let's put variables in for those shifts. All right. So those are the two options. Guess and check to find this. Plug in points to our guess and see if the points that we plug into are the points on the graph. The other option is a generic form and solve for the shifts. And this is the one I'm going to show. We showed option 1 in 6.2 lecture. Okay, so go back and watch 6.2 if you want to see option 1. I'm going to show you option 2, and that's what the book kind of does here. The book has a lot of different ways of doing these problems. Okay, so if you want to see alternate methods, go check out the book. So let's see this out. So I'm saying so frequently. So again, we said we know where left 2, it's log x, left 2, and reflected about the x-axis. So here's what we know. We know it looks something like negative, right, reflected about the x-axis, log of x plus 2, left 2. We don't know the vertical shift, so maybe there's a k here. We don't know stretching, so maybe there's an a here, right? These are the things that we don't know. So the thing is, we can plug in points to try to find them. And this is hard. This is going to be the hardest problem in the whole section, for sure, for most people. So what points do we know? We know the points -1, 1, 0, 0, and 2, -1. To -1 on the graph. So we're going to use these points and try to figure out, is there a vertical stretching? Is there a vertical shift? Let's find out. Use some of these points. All right. So let's plug in -1, 1. Then y is +1. And x is -1. If you type log of -1 plus 2 into your calculator, it equals 0. So this simplifies to just -a times 0 . I'm not a big fan of this method myself. But to be fair, I'm not a big fan of this, like doing these problems myself either. But they're important to teach. If you can do this problem though, you're going to be good to go. Remember, you can use your calculator for common log and natural log. Or you could transform this into exponential form to find that at 0. So again, let me do this. Let me not skip steps, right? This is just -a times 0 plus k, anything times 0 is 0. So we found that k is 1. We found that there is a vertical shift, up 1. Okay. So that's nice. So maybe there's still a vertical stretching, we don't know. But we definitely found that there's a vertical shift of 1. So let's plug in another point, right? Plug in another point. Let's plug in 0, 0. See if we can find a. So y is equal to 0. And x is equal to 0. So what does this look like? 0 is equal to -a times log of 2 plus 1. Now this equation looks nasty, but it's not, right? This is just a linear equation to solve for a. This is just a number. It's a messy number. It's an irrational number, but it's just a number. So if we just subtract 1, right, we get -1 equals -a log 2. and then divide by negative log 2, right? Then they cancel. We're just left with a is 1 over log 2. So guess and check would not be very useful here. I don't know if anyone would have guessed, oh, this is a vertical stretch by 1 divided by the common log of 2, right? So it's one advantage to doing it this way. So we're basically done, right? For example 5, I didn't say the domain, range, and asymptote. It took a whole page, but I wrote very big. I wrote in big friendly letters. So what's our final answer, right? We get y is equal to negative a times the common log of x plus 2 plus k, which is 1. And you cannot cancel these. These do not cancel. They do not combine. We'll talk about what you can do with these on Monday. All right. So just start with what you know on these problems. Start with what you know. Left 2 reflected. So there's going to be a plus 2 here. There's going to be a reflection. We don't know if there's a vertical stretch or a vertical shift. So we'll just put variables. We use these points and then just solved for these shifts. Okay? It's probably overwhelming right now, but if you do a couple of these problems, and again, even if you don't have to do the homework assignment, you should still look at some of the harder assigned problems because that's what's popping up on quizzes. All right? And after you do a couple of these, it should feel a lot more comfortable. Remember, you can do problems and say, wow, I'm completely lost. I don't know how to start this problem. Let me type up Discord. Hey, Jason, how do I start number 2 on section 6.5? And I will say, thank you, Jason, for asking. Here's how you start. Does that make sense? Yes, it makes sense. Or no, it doesn't make sense. And we can go to it from there. Okay? So please don't hesitate about asking questions as you're working through these. But you do need to do problems. Unfortunately, you will not just magically know everything by watching the lecture. I wish I were that good at lecturing, but I think it's impossible. How many more quizzes do you have? You have a quiz on Tuesday. Then you have an exam on Thursday. And then a quiz next Tuesday. And then a final exam that Thursday. You have 2 more quizzes. Okay, your lowest 3 get dropped. Which for many people will be quiz 8, the one you took yesterday. That was a tough quiz, though. That was a tough quiz. Sometimes when people get low quiz scores, I think, that sucks. I wish people would have done better on this section. And sometimes when people get low quiz scores, I go, yeah, that was a hard one. All right. Attendance question today is... I don't know. Something boring. Give me a season. Maybe your favorite season, maybe not your favorite season. Or bonus, not actually bonus. You could also, for attendance, tell me what is cooler, to say fall or autumn. All right. Anyway, real quick, we didn't talk about domain and range here. The domain here is the x values. That's negative infinity to 0. The range is the y values. It goes really flat here, but never flat enough. It does go all real numbers for the range. And the asymptote is x equals 0. So I'll make sure we answered that problem. Okay. So that's it for today. Have a great weekend. I estimated 30 minutes. Was a pretty good estimate if I do say so myself. Good luck. Bye-bye.